Welcome to Intro to Non-Measure Theoretic Probability, Part 0. So I'm going to assume you have calculus and some basic proof and linear algebra knowledge as well. But the first thing I'm going to discuss is something called structured randomness. What does this mean? Well, opposed to just pure chaos, structured randomness means that these experiments that we want to write mathematical statements about, they're actually going to converge in the long run to some sort of average. So let me just make this more clear. So we have an experiment here. If we do one realization of this experiment, we're going to get some sort of random outcome. Now, what happens if we take two of these things and average them together? So if we wanted to calculate the average of these outcomes, we just add them up and then divide by 2. Okay, now what happens if we continue playing this game? Do a bunch of experiments and then take the average. Intuitively, if you were to flip a coin, let's say, and assign the value 1 to heads and 0 to tails, let's say you get 1, 1, 0, 1, 1, 0, 0, 1, 0, and then we calculate the average. This is going to approach 0.5. But this is kind of what structured randomness is saying. It's saying that the average of this experiment will converge to some sort of limit. And not convergence in the calculus sense, but convergence in probabilistic sense. So we'll explore this in later videos. But this is what structured randomness is. So it's just saying that we can calculate the average, and the average will be something that's predictable. Okay, with that being said, let's get to our first important concept of today. So first thing I'm going to discuss is something called sample space. So to be clear, structured randomness is just an assumption we're making about the world so that we can actually study probability. Sample space is actually something very concrete we want to start defining. Sample space, we're going to usually denote as omega. Omega is the set of all possible outcomes. Okay, great. If we take an element of this set, this could represent just one realization. For example, rolling dice, omega equals 1 all the way through 6. So that's what a sample space is. Now we're going to define something else called a random variable. And just for shorthand, I'm just going to call it RVs. A random variable is just simply a mapping between our sample space and the real number line. So I'd say x is a random variable if x is a function between sample space and the real number line. For example, here I could do a mapping between heads and the number 1, as I mentioned before, and tails to 0. And in the dice roll case, I have to be a little bit careful here, but we can define a mapping, right? So I can say 1, we map to the value 1. Every value that we get on the dice is what we want the random variable to be. So this could be another example of a mapping. But in general, we didn't have to do this. We could say, we can define like a constant random variable even. No matter which value the dice roll takes, I'm always going to say the value of my random variable is a constant. So this is also a valid random variable, and this is called a constant random variable. So now that we have sample space and random variables, a natural next step in most probability textbooks and courses would be to define events. But in this case, we're not actually going to follow that. And this is because in this course, we're going to actually start with defining expectation before we define a probability measure. One advantage is that probability is actually just a special case of expectation. For those of you who are a little bit familiar with probability already, you can actually find that the expected value of an indicator variable on some set A is actually just the probability of A, where indicator is just 1 if omega is in A and 0 otherwise. So an indicator is actually a random variable. So when we take the expected value of an indicator variable, you can see that it's actually just the same as probability. So no matter if you define expectation first or probability first, you can always bridge the two with this indicator. This means that expectation is more general than probability, and meaning that we should probably do some axioms on expectation first. This way we can work with all sorts of random variables instead of limiting ourselves just in the world of indicator variables in the case of probability. The second main advantage, which is kind of related when we're dealing with continuous random variables later, it actually generalizes better if we have the expectation framework. Just for an example, so if I ask, what's the probability that y equals a? Some of you may know that this is actually just 0. Okay, what's the probability that y is between b and c? With discrete, we can say, okay, let's add them up. But now we have to say, use calculus, use integrals. Probability kind of changes in the case of discrete versus continuous, whereas expectation, we can just define some things on it first and then it will never change. So those are the two main advantages of defining expectation first.